There is one other place in the entire solar system where liquid falls from the sky, gathers into rivers, carves valleys through the landscape, and collects into seas large enough to have waves and shorelines and weather. It is not Mars. Mars lost its water billions of years ago. It is a moon. It orbits Saturn, nearly 1.5 billion kilometers from the Sun, and it is wrapped in a thick orange atmosphere so opaque that for centuries nobody had any idea what lay beneath it. Its surface sits at nearly 200 degrees below zero, cold enough that water ice there is as hard as granite and behaves like bedrock. And on that frozen ground, rivers run. Not rivers of water, rivers of liquid methane and ethane, falling as rain from orange clouds, flowing down through branching valley networks and pooling into lakes and seas near the poles. It is the only world we know of, apart from Earth, with a genuine cycle of evaporation, cloud, rainfall, and flow. A weather system, seasons, shorelines that advance and retreat. We have been there. In 2005, a small probe descended through that haze, photographed the landscape on the way down, and landed on a damp surface. It is still the most distant landing humanity has ever achieved. Tonight we go back, down through the orange, into the quiet, to a place where it rains. If you find peace in exploring the strange and distant worlds of the cosmos, consider subscribing to the channel. Let the slow, quiet weather of another world carry you somewhere restful as we drift together tonight. Welcome aboard, astronaut. Tonight, we drift through the cosmos. We leave Earth behind and travel outward, past the rusted deserts of Mars, through the long, empty stretch of the asteroid belt, past the great striped face of Jupiter with its slow, permanent storm. And then Saturn appears ahead of us. The rings resolve first, edge on and impossibly thin, then widen into a vast bright disk as we approach. Beneath them, the planet turns, pale gold, banded in soft cream and amber. Saturn holds well over 100 moons. Most are small, icy fragments, but one of them is enormous, and it does not look like the others at all. Titan hangs there in the dark, and it is not white, it is not gray. It glows a dull, hazy orange, and it has no visible features whatsoever. No craters, no mountains, no ice. Just a smooth, featureless ball the color of weak tea, wrapped in something the eye cannot penetrate. Tonight we will go through that haze. We will learn what it is made of and why nothing else in the solar system has anything like it. We will follow the probe that descended through it and see what it found. We will trace the rivers, measure the seas, and watch rain fall in slow motion in a gravity so gentle that a raindrop takes minutes to reach the ground. We will find the hidden ocean far below, meet a chemical mystery that nobody has solved, and ask what could possibly be living down there. Settle in. Let your shoulders drop. This is a quiet world, and we have time. Let us begin with the object itself. Titan is the largest moon of Saturn and the second largest in the solar system, beaten only narrowly by Ganymede at Jupiter. It is about 5,150 kilometers across. That makes it larger than the planet Mercury. If it orbited the Sun directly rather than Saturn, nobody would hesitate to call it a planet. But size is not what makes it remarkable. Ganymede is bigger, and almost nobody thinks about Ganymede. What makes Titan extraordinary is that it has an atmosphere, a real one, thick, stable, and permanent. This should not be possible. Moons are small, and small bodies have weak gravity, and weak gravity cannot hold on to gas. Our own moon has no atmosphere at all. Ganymede has the barest wisp. Every other moon in the solar system is essentially bare rock and ice exposed to vacuum. Titan has more atmosphere than we do. The pressure at its surface is about 1.5 times the pressure at sea level on Earth. That is roughly what you would feel standing at the bottom of a swimming pool. The air is about 95% nitrogen, which is remarkable in itself, because Earth's atmosphere is the only other one in the solar system dominated by nitrogen. The reason Titan can keep it is the cold. Gas molecules escape when they move fast enough, and molecular speed depends on temperature. At nearly 200 degrees below zero, the nitrogen simply moves too slowly to leave. Titan holds its air because it is freezing. But that's not all, because where all that nitrogen came from is a genuine question. Nitrogen is not something a moon simply accumulates. Titan formed from the cold material orbiting Saturn as the planet itself was assembling, and that material was mostly water ice, rock, and frozen compounds. Nitrogen gas is not easily trapped in ice at those temperatures. The leading explanation is that Titan did not start with nitrogen at all. It started with ammonia. Ammonia freezes readily and would have been abundant in the ices that built Titan. And ammonia molecules contain nitrogen. Break them apart with sunlight or with the heat of early impacts, and the nitrogen atoms pair up into the stable molecular nitrogen we see today, while the hydrogen escapes to space. The isotopes support this. The probe measured the ratio of 2 different forms of nitrogen in Titan's air, and the balance points toward an origin in ammonia from the original solar nebula, rather than delivery by comets later on. There is another surprise about Titan's history. In 2020, researchers combining years of tracking data found that Titan is moving away from Saturn far faster than anyone expected. About 11 centimeters per year, roughly 100 times quicker than standard tidal theory allows. If that rate has held, Titan formed considerably closer to Saturn than it orbits today, and has been slowly spiraling outward for 4.5 billion years. The moon we are visiting has been drifting away from its planet for its entire existence. Now, let's go deeper into how long it took us to see anything at all. Titan was found in 1655 by a Dutch astronomer using a telescope he had built himself with lenses he had ground by hand. It was the first moon of Saturn ever discovered, and for nearly 3 centuries it remained nothing more than a point of light. In 1944, an astronomer studying its spectrum found the signature of methane gas. That was the first indication that Titan had an atmosphere, and it made the moon immediately interesting. Then, in 1980, the first spacecraft arrived. Mission planners faced a genuine dilemma. The spacecraft was on a trajectory that could have carried it onward to Uranus and Neptune, continuing a grand tour of the outer solar system. But a close pass at Titan would bend its path and end that possibility. They chose Titan. The atmosphere was considered too important to skip. The spacecraft flew within about 4,000 kilometers of the surface and sent back its images. They showed nothing. A perfectly smooth orange ball. No features of any kind. The haze was completely opaque at visible wavelengths, and the cameras simply could not see through it. It was one of the great anticlimaxes in the history of planetary exploration. We had given up 2 planets and received a photograph of fog. But the other instruments gathered a great deal. The atmosphere was measured, the pressure determined, the nitrogen identified. And the tantalizing implication was immediate. At those temperatures and pressures, methane could exist as a liquid. Somewhere under that haze, there might be seas. But what happens when you finally send something down into it? The answer took 25 years to arrive. A large orbiter launched in 1997, carrying a small European probe bolted to its side. It reached Saturn in 2004, and on Christmas Day, it released the probe onto a collision course with Titan. The probe coasted alone for 3 weeks, dormant, with no way to steer. On the 14th of January 2005, it hit the upper atmosphere at around 6 kilometers per second, decelerated behind a heat shield, and deployed a parachute. Then it began the slow descent, drifting downward for 2.5 hours, taking photographs and measurements the entire way. The engineers did not know what it would land on. Rock, ice, slush, or open sea were all considered plausible. It had been designed to float, just in case. At first, the cameras showed only diffuse orange. Then, as the probe dropped below the main haze layer, the surface came into view. And it looked like a landscape. There were bright highlands cut by dark, branching channels. The channels narrowed as they climbed, joined as they descended, and drained toward a flat, dark plain. Anyone who has ever seen an aerial photograph of a river system on Earth would have recognized the pattern instantly. It was drainage. Something had flowed across that surface repeatedly for a long time.
And yet, there's more to this story, because the landing itself was full of information. The probe touched down at about 5 meters per second, roughly the speed of dropping from a low wall. The impact told us about the ground. Instruments recorded the deceleration and found a surface with a thin, brittle crust and softer material beneath. One of the scientists described it as being like landing on wet sand or on crème brûlée, firm enough to hold, but yielding underneath. Then the ground images came back. The probe was sitting on a flat plain scattered with rounded pebbles. They ranged from a few centimeters to about 15 centimeters across, and they were not sharp or angular. They were smoothed, and many were partly buried, with small depressions around them where something had flowed past. Rounded stones are one of the most reliable indicators in geology. On Earth, they mean a river. Angular rock fragments become rounded when they are tumbled by moving liquid over long distances, their edges worn away by repeated collisions. These pebbles are not rock. They are water ice, so cold that it behaves exactly like stone, and the liquid that shaped them was not water. Instruments also detected a rise in methane vapor immediately after landing. The warm probe was gently evaporating methane out of the damp ground beneath it. The surface was wet. The probe transmitted for about 70 minutes after touchdown, before its batteries failed and Titan went quiet again. It remains the most distant landing ever performed, and it is still the only one anywhere in the outer solar system. The journey continues to the haze itself and what it is made of. The orange fog that hid Titan for so long is not water vapor or dust. It is smog, genuine photochemical smog, produced by sunlight on an industrial scale, continuously for billions of years. The process begins high in the upper atmosphere. Ultraviolet light from the distant sun and energetic particles trapped in Saturn's magnetic field strike molecules of nitrogen and methane and break them apart. The fragments are highly reactive, and they immediately begin recombining into larger molecules. Ethane, acetylene, propane, hydrogen cyanide, benzene, and then larger and larger structures, chaining together into complex organic compounds with no fixed formula. Chemists call the resulting material tholins, from a Greek word meaning muddy. They are reddish-brown, sticky, and enormously complex, containing carbon, nitrogen, and hydrogen in tangled arrangements. These particles form a haze that begins hundreds of kilometers up and extends far higher than any layer of Earth's atmosphere. And because the particles are heavier than gas, they slowly drift downward. Titan is snowing organic material. Not water snow and not in flakes, but a continuous fine drizzle of complex carbon compounds settling out of the sky and accumulating on the ground. This has been happening for billions of years. The surface of Titan is buried under a layer of organic sediment, and every landscape we will visit tonight is built on top of it. Now, let's go deeper into how we finally mapped a world we cannot see. Visible light was useless, but there was another way. The orbiter carried radar. Radio waves at those wavelengths pass straight through the haze as though it were not there, bounce off the surface, and return. By sweeping the radar beam across Titan during dozens of close flybys over 13 years, mission scientists slowly assembled a map. It came together in strips, one pass at a time, gradually filling in a world. Radar does not produce a photograph. It measures how strongly each patch of ground reflects radio waves, which depends on roughness and composition. Rough terrain scatters energy back strongly and appears bright. Smooth terrain reflects the beam away like a mirror and appears very dark. In 2006, a radar pass over the northern polar region returned something startling. Large regions of near-perfect blackness, with sharp, complex outlines. Almost nothing in nature is that smooth, except a liquid surface. The shapes were unmistakable. They had winding shorelines, bays and inlets, islands, and branching arms extending inland exactly where river valleys entered them. They were lakes, hundreds of them. Later observations confirmed it beyond argument. When sunlight caught the surface at the right angle, the orbiter recorded a specular reflection, a bright glint off a flat liquid mirror, precisely like sunlight flashing off a lake on Earth. But what happens when we look at those seas closely? Titan's lakes and seas are concentrated near the poles, and most of them are in the north. The three largest are seas rather than lakes. The biggest covers roughly 400,000 square kilometers, which makes it larger than any lake on Earth. It is comparable in area to the Caspian Sea, and radar sounding suggests parts of it are over 300 meters deep. The liquid is a mixture, mostly methane and ethane, with dissolved nitrogen and traces of other compounds. The proportions vary from sea to sea, and even with depth. Radar could measure the depth of some of these bodies directly, which tells us something remarkable about the liquid itself. The radio waves passed all the way to the bottom and returned. That only happens if the liquid is extraordinarily pure and transparent to radio, far clearer than any body of water on Earth. There are shallower lakes too, many of them small, steep-sided, and roughly circular, sitting in raised rims. These look like they were formed by dissolution, where liquid slowly ate away at soluble organic material in the ground and created a basin, much as water carves sinkholes in limestone. And there are transient features. In 2013, a bright patch appeared in one of the seas, in a place that had been smooth before. It faded, then reappeared elsewhere later. Astronomers nicknamed it the Magic Island. The leading explanation is bubbles. As nitrogen dissolved in the cold liquid comes out of solution, it could froth to the surface and roughen it enough to reflect radar. Seas that fizz. And yet, there's more to this story, because those seas are part of a complete cycle. On Earth, water evaporates from oceans, rises, cools, condenses into clouds, falls as rain, runs downhill through rivers, and returns to the sea. It is the engine of our weather and the sculptor of our landscapes. Titan runs the identical system, with methane in the role of water. This is possible because of a coincidence of temperature. Water on Earth sits near its triple point, the narrow range where it can exist as solid, liquid, and gas at the same time. That is why we have ice, oceans, and clouds all at once. Methane on Titan sits in exactly the same relationship to its own freezing and boiling points. At Titan's temperature and pressure, methane can be a liquid on the ground, a vapor in the air, and a cloud in between. So Titan has clouds. They have been photographed drifting across the polar regions and gathering during seasonal changes. It has rainfall. It has rivers. It has lake levels that rise and fall. And it has seasons, though they are enormous. Saturn takes about 29.5 Earth years to orbit the Sun, so each Titanian season lasts more than 7 years. Over the course of the mission, scientists watched clouds migrate from one hemisphere to the other as the seasons turned, and saw some southern lakes shrink while northern ones stayed full. The same physics, a completely different chemistry, and a landscape shaped by weather, in a place where water is a mineral. Now, let's go deeper, because we watched those seasons change. The orbiter was in the Saturn system for 13 years, which is close to half a Titan year. That was long enough to see the Moon move from northern winter into northern summer, and the transformation was extraordinary. When the spacecraft arrived, the North Pole was in darkness and capped by a high atmospheric hood, a dense concentration of haze sitting above the winter hemisphere. The South was in sunlight, and clouds gathered there. Then, in 2009, Titan passed through its equinox, and the whole circulation reversed. Over the following years, the northern hood thinned, and the southern pole grew cold and dark. And then something remarkable formed above it. A vortex, a great swirling column of atmosphere spinning above the winter pole. Instruments found that the vortex contained clouds of a kind that exist nowhere on Earth. High in that spinning column, at altitudes where the temperature fell below 240 degrees below zero, molecules of hydrogen cyanide were freezing directly out of the air into ice crystals. Clouds of frozen poison rotating slowly above a dark pole. Meanwhile, the cloud activity that had gathered in the south migrated northward, following the sunlight, and the northern lakes stayed brim-full, while some southern ones visibly retreated. Titan has weather patterns that take decades to unfold. We saw one half of one cycle, and it is the only long-term record of another world's climate that we possess. The journey continues to what rainfall actually looks like there. Methane rain does not behave like water rain, and the differences are almost dreamlike. Titan's gravity is about 1/7 of Earth's, similar to our Moon, and its atmosphere is dense, considerably thicker than ours at the surface. Weak gravity pulling down, thick air pushing back. Both effects slow a falling drop. Calculations suggest methane raindrops fall at roughly 1.5 meters per second. A raindrop on Earth arrives at around 9. So rain on Titan descends at something closer to the speed of drifting snow. And from a cloud a kilometer up, a single drop would take more than 10 minutes to reach the ground. The drops are also larger. Surface tension and the gentle fall allow them to grow to nearly a centimeter across, roughly twice the size of the largest raindrops on Earth. Fat, slow, glassy spheres drifting down through orange air. And it is rare. Models suggest that in many regions, significant rainfall may occur only once in several centuries. Titan's weather is extraordinarily patient. But when storms do arrive, they are severe. Rainfall rates during Titan's methane storms are estimated to be comparable to intense tropical downpours on Earth, delivering enough liquid to flood dry channels and move sediment, which explains the landscape perfectly. Deep, well-carved valley networks, standing empty and dry for hundreds of years, waiting for a storm that will fill them in an afternoon. Now, let's go deeper into the great dark bands around the equator. While the poles hold the lakes, Titan's equatorial regions are dry, and they are covered in dunes. Radar revealed vast fields of them, long parallel ridges running for hundreds of kilometers, spaced regularly, rising about 100 meters high. They wrap around the Moon in enormous belts and cover something close to a sixth of the entire surface. They are shaped like the linear dunes of the deserts of Earth, and their form indicates persistent winds blowing from west to east. But the sand is not sand. There is no silicate rock exposed at Titan's surface to grind down into quartz grains. Instead, the dune material appears to be organic, the accumulated tholin haze that has been drizzling out of the sky for billions of years, compacted, broken up, and sorted by the wind into grains roughly the size of coffee grounds. Dark, soft, faintly sticky organic particles piled into dunes taller than most buildings, stretching to the horizon in every direction. There is one more oddity. The dune shapes indicate eastward winds, but Titan's surface winds usually blow the other way. The current explanation is that only rare, strong wind events during seasonal transitions are powerful enough to move the grains, and those storms blow eastward. So the dunes are not built by everyday weather. They are built by rare events, remembered in the landscape for thousands of years. But what happens when we look beneath the surface? There is an ocean down there, not of methane, of water. The evidence came from gravity. As the orbiter passed close to Titan, the Moon's gravitational field pulled on it, and Saturn's tides flexed Titan slightly. By tracking tiny changes in the spacecraft's velocity with great precision, scientists measured how much Titan deforms. A completely rigid body barely flexes. A body with a liquid layer inside flexes considerably more. Titan flexes a great deal. The measurements indicate a global layer of liquid beneath the ice. There is a second line of evidence. Titan's rotation shows small irregularities that are difficult to explain if the crust is locked to the interior, but straightforward if the outer shell is floating on something fluid and can slip. The ocean is thought to lie beneath an ice shell, perhaps 50 to 100 kilometers thick, and to be composed of water mixed with ammonia, which acts as an antifreeze and keeps it liquid at temperatures where pure water would freeze solid. It may be well over 100 kilometers deep, and it likely contains more liquid water than all of Earth's oceans combined. So Titan is layered in a way no other world is. Organic dunes and hydrocarbon seas on the surface. A crust of rock-hard water ice below them, and beneath that, a dark, salty, ammonia-rich ocean, sealed away from the sky. Two entirely separate liquid environments on one moon made of completely different substances. And yet, there's more to this story, because there is a mystery in the air, and nobody has solved it. Methane should not be there. Ultraviolet light continuously breaks methane apart in the upper atmosphere. The fragments recombine into heavier compounds, which drift down as haze and are lost from the atmosphere permanently. The process is one way. Methane goes up, tholins come down, and the methane never returns. Calculate the rate, and it is startling. At the observed rate of destruction, Titan's entire atmospheric methane supply should be exhausted in something like 10 to 30 million years. Titan is 4.5 billion years old. So either we are living at an extraordinarily unusual moment, or something is putting methane back. The most popular idea is that Titan has cryovolcanism. Not eruptions of molten rock, but eruptions of slushy water and ammonia from the interior, carrying dissolved methane up to the surface and releasing it. A few surface features have been proposed as candidate ice volcanoes, but none has been confirmed convincingly, and the evidence remains debated. Another possibility is that methane is stored in the crust as clathrates, a form of ice with methane trapped inside the crystal structure, and released episodically when conditions change. A third possibility is genuinely strange. Titan's atmosphere may not be in a steady state at all. Perhaps methane is released in enormous episodes separated by long dry periods, and we simply happen to be observing during one of the wet intervals. If that is true, Titan's rivers may have run and stopped many times. The journey continues to the question everyone eventually asks: could anything live there? Titan offers two completely different possibilities, and they are worth separating carefully. The first is conventional. The subsurface ocean is liquid water, rich in ammonia, in contact with a rocky interior that supplies minerals and possibly heat. That is not far from the environments we consider promising elsewhere. If life needs liquid water, Titan has an enormous amount of it, and it has had it for billions of years. The difficulty is access. That ocean is buried under 50 kilometers or more of ice, with no obvious pathway to the surface, which makes it extraordinarily hard to study. The second possibility is far stranger, and it is the one unique to Titan. Could something live in the methane? The surface has liquid, abundant organic chemistry and available energy. What it lacks is water, which every organism on Earth depends on absolutely. Water is an excellent solvent because its molecules are polar. Liquid methane is not polar, and biochemistry as we know it simply does not work in it. But researchers have asked whether a different chemistry could. One proposal describes a cell membrane built not from the fatty molecules our cells use, but from small nitrogen-bearing organic compounds that could form stable, flexible structures in liquid methane. Encouragingly, one of the required compounds was later detected in Titan's atmosphere by radio telescope. This remains entirely hypothetical. No one has demonstrated such a membrane, and there are serious objections. The extreme cold slows chemistry enormously, and biology needs reactions to proceed at some workable pace. But Titan is the only place where the question can even be asked. And yet, there's more to this story, because Titan may be valuable for a completely different reason. Even if nothing lives there at all, it may be a working model of the young Earth. Before life appeared here, our planet had an atmosphere without oxygen, rich in nitrogen, probably containing methane, and exposed to unfiltered ultraviolet light. Under those conditions, some researchers think early Earth was wrapped in an orange organic haze not entirely unlike Titan's. That haze period would have been brief, and every trace of it is long gone. Earth's surface has been recycled by plate tectonics, weathered by oxygen, and rebuilt many times over. The chemistry that preceded biology left almost no record. Titan preserves that stage permanently. The Moon is running the same fundamental process at planetary scale continuously for billions of years. Simple molecules are being assembled by energy into progressively more complex organic compounds, which accumulate on the ground in enormous quantities. And crucially, nothing is eating them. On Earth today, any interesting organic molecule produced in nature is consumed almost immediately by something hungry. Prebiotic chemistry cannot be observed here because biology got there first and never stopped. Titan has no such competition. Its organic inventory has been building up undisturbed since the solar system was young. So even in the least exciting case, where Titan is completely sterile, it is still the largest and longest-running experiment in prebiotic chemistry available to us. A place to see what chemistry does on its own, given 4.5 billion years and no interference. Now, let's go deeper, and imagine standing there. The first thing you would notice is the light. Titan receives roughly 1% of the sunlight Earth does, and the haze absorbs and scatters most of what arrives. Daylight on the surface is perhaps 1,000th of a bright day here, about as bright as Earth a few minutes after sunset. The sky would be a dim, uniform orange-brown. No blue, no stars, because the haze blocks them. And you would never see Saturn, despite it filling a huge portion of the sky above the clouds. The haze hides it completely. You would not need a pressurized suit. The surface pressure is close to Earth's, so your body would be comfortable in that respect. What you would need is extreme insulation and a supply of oxygen. The cold is the danger, not the pressure. The air would feel thick, almost like standing in water, and sound would carry well through it. And here is the detail that delights everyone who learns it. Titan has low gravity and a dense atmosphere, which is the ideal combination for flight. A person wearing a pair of modest wings strapped to their arms could genuinely fly by flapping. Not glide, fly under their own muscle power. You could step off a dune, beat your arms, and stay airborne over a landscape of black organic sand under an orange sky, beside a sea of liquid methane. It may be the only place in the solar system where a human being could do that, and the flight would be as slow and gentle as everything else on this moon, astronaut. In 1/7 of Earth's gravity, a jump lasts several seconds. Falling feels like sinking through water. Every movement would carry that same underwater quality, unhurried, cushioned, drifting. Sound would behave strangely too. The thick air carries voices further and lowers their pitch, so speech would come out deeper than you have ever heard it. Picture it for a moment. Standing on a soft, dark dune in permanent dusk, a still orange sky overhead, a shoreline in the distance. No wind, no sound at all except your own breathing. Somewhere above, drops of methane are drifting down so slowly that you could watch one fall for 10 minutes before it reached your glove. It is a quiet place, possibly the quietest place we have ever mapped. But what happens next? We are going back, and the mission is unlike anything ever flown. Because Titan has a thick atmosphere and low gravity, flying there is remarkably easy. A rotorcraft needs only a fraction of the power required on Earth to lift the same mass. So the next mission is not a rover. It is a nuclear-powered flying machine with 8 rotors, roughly the size of a small car, designed to spend years hopping across Titan's surface. Rather than crawling a few kilometers, as wheeled rovers do, it will fly tens of kilometers in a single flight, landing at a new site, spending days studying the ground beneath it, then taking off again. Over its planned mission, it will visit dozens of separate locations. It will land first among the equatorial dunes, then work its way toward an impact crater where, long ago, an impact would have melted water ice and mixed it with the surface organics, liquid water and complex organic chemistry together for perhaps thousands of years. That is about as close to a natural laboratory for the origin of life as we could hope to find. The journey there takes years, and the science will unfold slowly across the following decade. It is a mission built entirely on patience, aimed at the most patient world we know. Somewhere in the 2030s, if all goes well, something built by human hands will lift off from an alien dune field and fly. Take a quiet moment to reflect on what this means, astronaut. There is something disarming about Titan, and it is worth naming. Almost every other world we have visited is hostile in a way that feels foreign. Venus crushes and burns. Jupiter has no ground at all. Mercury is a bare rock swinging between extremes. Even Mars, the most familiar of them, is a cold, dry desert with an atmosphere too thin to matter. Titan is different. Titan is recognizable. It has clouds and weather. It has rivers with tributaries, and lakes with bays and islands, and dunes shaped by wind, and pebbles rounded by flowing liquid, and shorelines that shift with the seasons. If you were shown a radar map of it without being told what it was, you would assume you were looking at somewhere on Earth. And yet, nothing about it is the same. The rock is ice. The sand is organic dust from the sky. The rivers are methane. The rain takes 10 minutes to fall. It is our own planet's grammar, written in an entirely different vocabulary. That may be the most quietly profound thing Titan tells us. The processes we think of as belonging to Earth, erosion, rainfall, weather, coastlines, are not properties of water or of our particular chemistry. They are what happens whenever a world has liquid, gravity, and an atmosphere. Nature does not need our ingredients, it only needs the conditions, and given those, it builds landscapes we would recognize anywhere. We drift upward now, away from the dunes, back through the orange haze, watching the seas at the pole shrink into dark patches, then vanish beneath the smog. Titan closes behind us, featureless again, a soft amber ball turning slowly beside Saturn's rings. From out here, nothing suggests what is down there. No rivers, no shoreline, no weather, just quiet orange. It will keep going exactly as it is. The haze will keep falling. The dunes will wait for their rare eastward storms. And somewhere near the North Pole, methane will keep evaporating from a sea larger than any lake on Earth, rising into clouds that may not rain again for 100 years. There is no hurry anywhere on that moon. Nothing there has ever been in a hurry. Close your eyes now. Let yourself sink into that same slowness. Somewhere far away, a raindrop is falling, taking its time. Mission complete, astronaut. The stars will wait for you. Good night.